Hello everyone, I'm Jimmy Koppel, and I'll be talking about something I've been working on quite a while, automatically deriving control flow graph generators from operational semantics. Joint work with my advisor Armando and my former student in Jackson. So control flow graphs might sound pretty boring. Well, we would have said that before the last talk at least, but they're an important part of compilers, and this work is part of a much larger, grander vision, which is when you write a new language, you need all these little pieces of infrastructure for it. Simple table generators, code generators, static analyzers. And I don't like having to kind of re-implement the same algorithm from the same papers and books for different languages. And it should be theoretically possible to derive all these given the syntax and semantics of a language. But for some of these tools, they're pretty far from what we see in the syntax and semantics. Sometimes it's kind of easier to see it. The symbolic executor kind of looks like just running it. And so, in fact, the K-framework people have already managed to derive these. But today I'll be talking about something where it's much harder to see how it has any resemblance to the Greek letters. And now I'll be presenting Mandate, the world's first control flow graph generator. It takes as inputs the operational semantics programming language, and it gives you very readable code, actually quite similar to what we actually hired a person to write control flow graph generators in the same language. And indeed, they're quite similar, except he was low paid and got a lot of stuff wrong. And then we can just run them and get control flow graphs. And we were able to do this not for big languages like C and Java, but not for IMP either. We did this for Tiger and MIT script, two languages from compilers classes. So now I'm going to try to do what in a few minutes, which took a long time to do for viewers, to care about control flow graphs. So what does a control flow graph look like? So the standard answer, so the most common answer, if you take an undergrad, is just taking a compilers course, it's likely to give you one of these things. This is the basic block control flow graph, and it's really nice because it has few nodes and a small memory footprint, so it's very fast, you can compile fast. But it's also a little inelegant to squash things together like this. So in the previous talk, I believe, used this kind, the statement level, where you have one node per statement and you just don't squash together straight line code. But there's more options. So one that I like a lot is the expression level control flow graph, because if you're writing a static analyzer, not on 3-address code, but on an adaptive syntax tree, it's really, really nice to be able to say exactly what is true about your program and the abstract state before and after every single inner expression. So none of our static analysis frameworks use this kind. A little more exotic and less implemented is this kind, probably none of you have thought of before, which is, suppose I wanted to write a static analyzer that's going to take this code I have here and prove that it always outputs balanced parentheses. It's kind of specific, but this is very, very easy to do if you have in your states which path it's going down, because then with this if statement, do the same if statement twice, you just remember which one you did. It's straight line code now, and it's very trivial to prove that it prints out balanced parentheses. This is kind of getting towards a model checker, and we usually don't implement control flow graph generators give us these because they're very application specific, but why not? Maybe we had a control flow graph generator, we could do this. And so really we need all of them. There are a bajillion different static analyzers you could write, each of which could use its own control flow graph, which partitions the program state exactly the right way to suit that static analyzer. And then if I want to take 20 of these analyzers and run them at the same time and have them interoperate, then I need something that's partitions the program state in ways that's good for all of them. So we want infinitely many control flow graph generators. So that's why we want a control flow graph generator. So starting to do this. So Richard Feynman gives a very great general algorithm for solving problems, which is to write down the problem, think really hard, and then write down the solution. And so inspired by him, we're going to solve this by defining control flow graph and then implementing the definition. Because it turns out that after 60 years, no one's really defined control flow graph from first principles. Here's some Greek, here's semantics. Do you see the control flow graph nodes in that? I didn't, and I thought about this stuff a lot. So it's not at all obvious how to go from this to control flow graphs. What do these things even mean in terms of semantics? So, I mean, the easy answer is, oh, like a control flow graph node is just a subtree program. But if you really did that, then like every time the word prints appears in your program would be the same node, which is clearly not the case. And just the continuations, at first I thought, oh, a control flow graph node is like a continuation. It's like the stuff that happens after. But then there are also things that where the same thing happens after two lines, but somehow don't merge them. As a little spoiler, it's both. So there's a couple of big ideas they're going to use to go from the Greek letters into the smaller control flow graph. And the first one is that actually the structural operator semantics is not the right way. It's kind of too far. First, we want the abstract machine instead. This is a quick primer on abstract machines. And the abstract machine state has two things. It has the current subterm you're focusing on and a continuation. Now, sometimes you have some more stuff in there, but these are the two basic things. And then when we step, well, for this one, we're going to descend into E1. And then after we're done evaluating E1, we plug it into whole plus E2. So we're going down the stack. So some abstract machine rules for addition. And these actually already have a notion of program point in them. It's already closer to control flow graph. And so our first step is we're going to convert the operator semantics into the abstract machine. And it turns out that the times when we can't do this, when there is no abstract machine, actually correspond to the languages where control flow jumps around too much, and the control flow really isn't modeled as a transition system. There is no control flow graph. And this is great. So all we need to do is just go to the literature, look up how to do this conversion, and then we're halfway there. Except that I tried that, and surprisingly, there was not already an algorithm for this, so I had to build one. And it's like crazy because there's been all this work, mostly by Olivier Danby and his students, on how to take different formalisms for semantics and interconvert them. And so wait, he hasn't done this? And there is even I think invited paper from this conference about 15 years ago where it sounded like he did this, but actually he only did that on a single example. It was not an algorithm. So when I visited him in Singapore, I asked him about this. He told me many things, including some advice that I used to help format the title slide of this talk. But he also told me he personally did not care about automated algorithms. If you know how to do it for one, you know how to do it for all. But that's not good for me because I actually want a system you can run. So I had to do it myself. So I'm going to say a little bit about how we do this, which we have a pretty nice approach. That's pretty general, and some of the things are really hard in the other path are really easy for this. Just say a few words about that, which is, here we have some SOS rules for addition and the corresponding abstract machine rules. And I'm really tempted to think, oh, there's 3 SOS rules, 3 abstract machine rules, clearly these match. The first rule is the first rule of each, right? And so actually, if you squint at it, if you look a little harder, that's not the case. Because in fact, the first abstract machine rule, we're just descending into saying, I'm going to evaluate E1 first, E1 plus E2. That actually corresponds to the first half of the first congruence rule. And the next rule corresponds to 2 halves of 2 different rules, and so on. And so this is actually the big idea of the path that we take for our conversion algorithm, which is we have an intermediate representation where each of these arrows gets its own rule. So we're taking the SOS rules, splitting it apart, and then we fuse them back together a different way. So the abstract machine is giving us the notion of current program points. And so the first steps for every language, we convert the operator semantics into an abstract machine. And then we have a cute idea. So here is an if statement. And I want to get to statically control flow graph. Let's just say that E, my control flow is going to depend on what that value of E is. I'm going to say it's star. It's something. It's a value. Something. And then I can take verbatim the abstract machine rules I have and say, well, this thing could match that. It's going to evaluate to there. And then I have different rules for if it's true or false, and I don't know which one it is, so both of them could match. So let's This is our graph. And now we're already getting something that kind of looks like a control flow graph. And I can actually say that these abstracted active machine nodes are CFG nodes as a definition. And these actually kind of correspond to something you would see in a handmade control flow graph. Like first, we have the input node, the in node of the if statements. Down here, we have the in nodes of the then and else statements. But then this thing in the middle, which I get from remembering these rules, is also corresponds to the in node of an if statement. But of course, I can just squeeze things together afterwards, and so it's a kind of heuristically merges together, and now we have beginnings control flow graph for this if statement. So that's a big idea, but it's still in code it's going to give me a graph, not like run these rules like an interpreter and give me a graph. And the second insight is like, I gave you this for one if statement in one context, in one continuation, but the work I just did would look pretty similar for any other if statement, any other context. So there's some way to turn things into symbols where we can evaluate what this process can look like for all if statements ever and get a control flow. And there is, so I just put in symbols. So here's a while loop where E and S are the conditioned body. It's going to be any condition, any body, any continuation, any context. Here I do environments, so any binding of variables to values. And now I can run the rules on this. So I be sure the while to an if. I run the if. I run the if. So okay. So yes, I'm running the if. Something's going to evaluate the condition. That's the dashed line. So I run the if, and either going to do the body or go to the end. And at the end, I suddenly find myself back at the beginning, and to infer this back edge just from following the rules, not from any special knowledge. Now I squeeze some of these things together and label them. And to get the code, I can just read off the code from this graph pattern. Graph pattern describes control flow of all while loops in this language, period. And I just write some code that prints out these edges. And bam, I'm done. Now, as I did say earlier, we actually want a huge family of control flow graph generators, not just one. So how do I decide what becomes a star? What things I skip over? Well, I write a little bit of code for that. To say that all values become star, that's saying I don't care what value it is. It's going to give me an expression level control flow graph. To say all expressions become star, it means I'm not going to have internal nodes for that expression. I just say skip over it. The code is a little bit more, but not that much. And so these two different kinds of abstractions are giving me different control flow graph generators at different levels of coarseness. Then, of course, I also can always just take nodes and merge them willy-nilly afterwards. So that's the second parameter. And from these two parameters, the abstraction projection, I can get all kinds of control flow graph generators, period. And so that's a system. We take the semantics, we get after machine, we take in the abstraction and projection, just a little bit of Haskell code, then we get a syntax-directed control flow generator out of it, give you the program, give me the program, bam, there's a control flow graph. So we did this. We generate control flow generators, multiple kinds, just to make sure it works. We did actually have to use them somehow, built a couple of small static analyzers on them. So it just proves these are actually good for something. I just want to say a little bit about one of the things it did, which is the most complicated CFG node generator it did. So for loops in Andrew Appel's Tiger language, a little complicated, which is they're actually like 4 interval loops, for A equals B up to C do D. And the D sugar is something it's not actually exactly big, but is a lot of AST nodes. And so when you actually write this out, it's the control flow, the graph pattern is about 43 nodes, and yet we still manage to get very short and readable code out of it. So, and now I can finally summarize it all into my definition of control flow graph from first principles, which is just as we all know that monads are monoids in the monoidal category of end-functors. So control flow graph nodes are a projection of the transition graph of abstracted abstract machine states. And by the way, in an earlier draft of the paper, I used the word abstract 6 times in the same sentence in the abstract of my paper. So we're pretty excited about this technique, this technology. The ideas in here we think can do a lot of other things with partially evaluating semantics into tools. And I'm also very excited about if you give me a black box interpreter of a language, can we derive the semantics and then run this? So we go from a black box artifact into useful tools. I'll encourage you to check out the paper. We have a lot more details in there. There are some major parts that I glossed over and didn't mention, like what we do. Certain kinds of control flow graphs, we can't get a syntax-directed thing because they're not syntax-directed. But we actually prove some correspondence between some things. There's an automated termination theorem. There's an automated termination proven there. Prove that if one thing terminates, then another process always terminates for all inputs. It's pretty cool. And so yes, so that is the world's first control flow graph generator. Thank you.